Did science just prove multiple realities? Oh, and now time can run backwards. Seriously. 24 hours of epic weirdness in the world of quantum physics. Two great strides in quantum physics have been reported in the past 24 hours. 1. MIT Technology Review reports that reality may not be objective, that different observers may witness the same event and both be 100% right about what they witnessed, thus possibly proving the existence of multiple realities. And 2. Nature reports that scientists in America and Russia have demonstrated that time can run backwards. Ow. Yes, my brain hurts, frequently. Let's tackle the less momentous event first, the demonstration that time can run backwards, thus presenting an existential threat to the second law of thermodynamics. The second law of thermodynamics states that the state of entropy of the entire universe, as an isolated system, will always increase over time. The second law also states that the changes in the entropy in the universe can never be negative. The article in Nature is a bit of a slog for non-scientists like myself, so Newsweek thoughtfully made things clearer for the rest of us. In a study published in the journal Scientific Reports, scientists from the US and Russia have experimentally demonstrated time reversal, sending a qubit from a more complicated state to a simpler one. The algorithm they suggest changes the quantum developed state so it starts to develop back in time. Doing this magic with the developed state of ink, we will see that after the same time needed for the dissolving of ink in the water, the ink will again combine back into the original drop, study author Andrei Lebedev told Newsweek. This is exactly what we did in our work, where the drop of ink is state of 3 qubits, and the water is a Hilbert state of the quantum computer. Boldface mind, magic, indeed. To be sure, this study only demonstrated this effect on the quantum level. There is thus far no indication that this effect can be duplicated on anything above the quantum level, so we husbands can forget about unsaying that really dumb thing we said before getting the silent treatment from hell. Girls know what I mean, but for guys who've never been in a long-term relationship with a girl, well, you'll learn the hard way. We always do. But I digress. Since the effect has only been seen on the quantum level, until such time that this can be put into practical use, we should see this in the same vein as the discovery of the Higgs boson. It's incredible and it pegs the cool meter, but not yet of practical value beyond that of scientific understanding. Or, to put it another way, not much. Yet. In my opinion, the more important of the two discoveries was the report that reality is not objective, that what one observer sees in an event may literally be in a different reality from what was witnessed by a second observer. Explaining this requires going deep into the quantum weeds for a while. Remember Schrödinger's cat? Here's a simplified version from whatis.com. A living cat is placed into a steel chamber along with a hammer, a vial of hydrocyanic acid and a very small amount of radioactive substance. If even a single atom of the radioactive substance decays during the test period, a relay mechanism will trip the hammer, which will in turn break the vial of poisonous gas and cause the cat to die. In the experiment, the observer cannot know whether or not an atom of the substance has decayed, and consequently, does not know whether the vial has broken and the cat has been killed. According to quantum law under the Copenhagen Interpretation, the cat will be both dead and alive until someone looks in the box. In quantum mechanics lingo, the cat's ability to be both alive and dead until it is observed is referred to as quantum indeterminacy or the observer's paradox. The logic behind the observer's paradox is the proven ability of observation to influence outcomes. Boldface mind, see that last sentence. It is proven that observation itself influences outcomes. We also know that when two particles are entangled, when the state of one particle is changed by observation, the other entangled particle is changed as well. Bear in mind, too, that there is no limit of either distance or time when it comes to quantum entanglement. Yes, a particle can be entangled with another particle in the past. In other words, when you go out and look at the stars at night, the light you see are photons from stars many light years away. Let's say you're looking at Betelgeuse, the red giant that is the right shoulder of the Orion constellation. It's about 520 light years, plus or minus 73 light years, away. If one of those photons striking your eyeball is entangled with a photon in the boiling hell that is the surface of Betelgeuse, then your observation of the photon striking your eyeball not only changed the state of that photon, but also at the same instant changed the state of its entangled partner photon in the surface of Betelgeuse 520 light years away. Is it weird enough for you yet? Wait, It gets better. Okay, so we've established that the observation of a quantum particle changes the state of that particle. Ready to have your mind blown? What happens if two people observe the same particle at the same time? The experiment involves two people observing a single photon, the smallest quantifiable unit of light that can act as either a particle or a wave under different conditions. The photon can exist in one of two alignments, but until the moment someone actually measures it to determine which, the photon is said to exist in a superposition. Both conditions are true at the same time. In the thought experiment, a scientist quietly analyzes the photon and determines its alignment. Another scientist, unaware of the first's measurement, is able to confirm that the photon, and thus the first scientist's measurement, still exists in a quantum superposition of all possible outcomes. As a result, each scientist experienced a different reality. Both are technically true, even though they disagree with each other. Bringing this idea from thought experiment to reality involved an experimental setup with lasers, beam splitters, and a series of 6 photons that were measured by various pieces of equipment that stood in for the two scientists. Other researchers previously devised the experimental setup, according to MIT Tech, but this is the first time that anyone managed to pull the experiment off. 2 different observers, 2 different outcomes, 2 different realities, and both are right. This essentially proves the Wigner's friend thought experiment, if anyone still wants to wade even deeper into the weeds. But it's about to get weirder yet. Here's a question. Now that each scientist observed a different reality, is either one still in the same reality as before? Or are both in realities that have branched away, if infinitesimally so, from the one they shared prior to the observation of that photon? The thing is, when the scientists each observed the change of state of that single photon, the event didn't happen in a vacuum, for all matter and energy are made up of particles and waves that change state all the time. Observation of photons by human beings changes the state of those photons, but is human observation is required in order for the states of photons or particles to change? From livescience.com, the rules of quantum physics state that an unobserved photon exists in all possible states simultaneously but, when observed or measured, exhibits only one state. So does this mean that quantum particles cannot change state until they are observed? Of course not. The most popular answer, formulated around the time Schrödinger produced his equation, is known as the Copenhagen Interpretation. Named after the home city of one of its pioneers, Niels Bohr, it says that a particle's state before observation is fundamentally, intrinsically, insurmountably uncertain. If the wave function says a particle could be here and there, then it really is here and there, however hard that is to fathom in terms of everyday experience. Only the act of looking at a quantum object collapses its wave function, jolting it from a shadowy netherworld into definite reality. The article goes on to describe problems with the Copenhagen interpretation, and then describes 3 alternatives. Alternatives to the Copenhagen picture fall broadly into 3 categories. One is that the wave function picture is not a complete description of reality. Decades of rigorous experiments have shown, however, that any additional bells and whistles would have to operate faster than light, breaking perhaps the most fundamental law of physics. A second possibility is that wave function collapse doesn't happen at all. Every possible outcome of an observation actually comes to pass in its own separate universe. This is the many worlds interpretation. See, Who Killed Schrödinger's Cat? The many worlds theory also creates almost as many philosophical problems as it solves, so Sudarsky began with a third option, that wave functions are real things and do indeed collapse, but randomly, by themselves. Something like a measurement occurs, but without anybody actually measuring, says Sudarsky. It doesn't need a human observer, so this process is known as an objective collapse. Ellipsis. Objective collapse would be rare, but catching. Wait for a single particle's wave function to collapse and you could be waiting longer than the age of the universe. Group many particles together, however, and the chance swiftly escalates. With a few billion particles, you might only have to wait a few seconds for one wave function to collapse, and for that to set the rest off. Boldface mine. The author clearly prefers the third alternative and makes a sensible case for its veracity, but the experiment described at the beginning of this article may have proved the second, the many worlds interpretation, MWI. Look at the bolded sentences above. Every possible outcome of an observation comes to pass in its own separate universe. It should be noted that there are different versions of MWI, and that this particular version of MWI was first described by Bryce DeWitt in 1970. It essentially states that everything that can happen, does happen, beginning at the quantum level, with quantum particles continually existing in every possible state, and so affecting every single possible result above the quantum level, and that each and every different state of every quantum particle in existence exists in its own reality. Yes, this would mean that there is a reality wherein Stephen King writes best-selling children's nursery rhymes, and Donald Trump, Ph.D., is a world-famous astrophysicist comedian even though he's confined to a wheelchair by ALS. And he's married to a transgendered man named Nancy Pelosi and loves him dearly. But wait, there's more. If this version of MWI holds true, then it may require that there is a different reality for every different combination of states of quantum particles in the universe. In other words, quantum particle Alice here on Earth is in state 0, while quantum particle Bob over in Betelgeuse or Andromeda or wherever is also in state 0, but also shifts to state 1, and there would be a separate reality for each combination of Alice and Bob, which combinations would create even more branches of reality whenever Alice or Bob change state again. And this has been going with every single particle or wave every instant that any such particle or wave changes state, since at least the beginning of the Big Bang. If this sounds beyond ludicrous, look again. Now for the first time, Massimiliano Proietti and fellow physicists have performed this famous quantum physics thought experiment for themselves by creating two alternative realities and then comparing these two worlds. After their experiment, the physicists determined that Wigner was absolutely correct with his suggestion that two people can disagree on the realities that they are witnessing, showing that even simple and objective facts can't be agreed upon. There is one last caveat from the same article. It is important to remember that this new research has still not been analyzed by other academics just yet, but will no doubt be thoroughly studied in the future. So it's not certain yet, but if it's verified, there may very well be a reality where you and your spouse and kids are getting dressed, eager to go see Dr. Donald Trump and his spouse caregiver Nancy Pelosi show you the wonders of the universe from his wheelchair at a planetarium on the south side of Chicago.